start class 2 of deterministic network calculus. So today we'll start with basic. So last class we we looked at motivation and introduction to deterministic calculus and what we'll be doing in this course. So today we'll start the basics on uh, how do you model and stuff. So today we'll look at basic models, single server, single flow system. Right. So in the introduction, maybe you've understood that network calculus is basically a theory where we try to find upper bounds on performance evaluation metrics or on performance metrics of network analysis. So what are those performance metrics? They are delays that the flow can see, or the queue buildup or the backlog in the networks. So these are the main motivations. So main motivation is calculate upper bounds on performance metric, right? So what are the performance metrics? The performance metrics are delays and backlogs. So basically, before going into seeing how we calculate these, we'll see how we model any real system which has a network or which has a queuing property using network calculus. So the modeling of the data that circulates in the network, or the modeling of the process, how the data is being processed in the servers. So this basically justifies the initial part of the course. So this will be only one class or two classes on modeling part. Next, we'll get into the math of it, and after that, we'll use the math to again come back to real life and real systems and see how what happens if we change some properties of the real systems. So basically, we'll be looking at some modeling properties. So before going into modeling properties, let's see. So you have a system. The system will have some properties, right? Now, that system, if it is a real system, suppose capital sigma is a real system. This real system will have real life properties. Now, based on the real life system, you come up with a theory. Now, this theory, it has a model M, and this model M will show some properties, right? Now, what you want is you want to model the real life system to your theory. This is a model, right? And this mathematical model of your real life system will have some mathematical properties. So this is a formal model. Will have some formal properties. Right. Now we want to see how good does the real life properties map to the formal properties. So what we want is we want all the formal properties to be mapped to the real systems properties, right? If we even actually don't know what are all the properties of the real system. We can only observe some of the properties that the real system can have, right? Yeah. So what we want to guarantee is, so if I make a model, right, it will have some formal properties. These formal properties needs to be inculcated in the real life system properties. I may not inculcate all the properties, but even if I can inculcate only some of the properties in the modeling part, then I am in a good enough state to start analyzing the model so that I get results on the real life system. So what do we want to ensure? We want to ensure that uh, what do we want to ensure? Right, that is the basic question. But this is based on the modeling part. Like the modeling, what do we want to ensure? We want to ensure that if model states that phi happens or phi is satisfied, then P is also satisfied. Right. So this is how we want to develop the theory of modeling a real life system. So first, before going into modeling of a real life system, we'll look at some very basic uh, block in a communication network. So that is known as a constant rate server, right? So as the name suggests, a constant rate server is a server that transmits exactly r bits of data per unit time. So it is the rate at which it is serving packets is constant. So it serves r bits of data per unit time. So basically, the aim of the whole network calculus is to find upper bounds on delay and uh, all. So before that, we need to make some assumption that what we have is we have a server S, right? There is an arrival flow A with some properties. There is a departure B. We want to find delay bounds, right? Under the assumption that the the scheduling policy for the single flow is FIFO. So whichever packet or whichever unit of data comes first to the server is served first. There are no priorities or anything. Whichever comes first, so is being served first. So what does FIFO mean? FIFO means it is a first in, first out system. What happens if we neglect this assumption and we have some priority based stuff? That we'll see later. But for now, for the basic modeling, we will start with the very simple case of constant rate server. And also we'll have the assumption that the packets are served in a first in, first out mode. Right. So before trying to find the delay bound and all, we'll try to introduce some notations. Okay. So basically, T is your time. Any letters of T, those all I'll be using for time. Okay. AT is the total amount of data that arrives to the system. So arrival, this AT is an of arrival, that arrives to system in the interval 0 to T. Similarly, DT is the total amount of data that depart from the system in the interval 0 to T. Now, the one of the important points is keep in mind how I denote the interval. It is a closed and then it's an open. Now, why do we use this kind of notation? I'll let you know. So I'll let you know why we use this type of notation. We'll have a discussion on it. Okay. So okay. So one more assumption. So one more assumption is there is no loss or creation of data in the server, right? So basically, no data is being lost in the server. Like once the data comes, it has to go out from the server. It can't go anywhere else, right? Creation of data. So the server can't just randomly create its own data and try to send it. Like it has to send the packet that it gets. It can't create new data. Okay. And one more assumption is initially the system is empty. So what does this mean is A0 equal to D0 equal to 0. So we want our model to satisfy these assumptions. Okay. Um, we'll call A as the cumulative arrivals and we'll call D as the cumulative departures. So in the last class, okay, so these are the basic assumptions. Now I'll just try to tell you what we try to do is, so you have your time axis and your data. Okay, so suppose, yeah, so you have some arrival traffic. So this could be some arrival traffic. This could be one arrival traffic. This could be one arrival traffic. This could be one arrival traffic. So in deterministic network calculus, what you do is you upper bound these all arrivals the deterministic function, right? So what that means is no arrival process that you have would be violating this arrival. Every arrival sample path would be below this arrival path. And this is known as an arrival curve. This is what we saw last time. Similarly, there will be many departure processes, right? Now, departure processes will always be less than or equal to the arrival process. These are the sample paths of the departure process. So now you want to bound the departure process with a load, right? So this is your service curve, minimum amount of service that you can guarantee. We don't want any departures to be less than the service curve. Now, given these two, what we can do is at each point, we can try to find out the delay, that maximum delay that the packet will see, because the only information that you know is the deterministic envelope of all the arrival curves. So you have 100% surety that the arrival curve will not be violating the envelope. Even the arrival curve bounded above, it will be bounded above by an arrival curve, it will be bounded below by a service curve, right? And to calculate the delay at each point, you just need to calculate the horizontal distance. Okay, so yeah, we'll come into that, but this is basically the whole crux of deterministic network calculus. Now, if you go into stochastic network calculus, which I'll be taking in coming up courses, there you'll see that you allow the sample paths to violate the envelope, but then you have to characterize the violation probability by some metric. So that is a whole separate topic. First, we'll discuss about deterministic, and then we'll go there. Okay. So where were we? We were in the arrivals, cumulative arrivals, and cumulative departures, right? Next. Okay. So now let me tell you something about backlogged period of a server. So a server is said to be backlogged if during a time interval, server is never empty. right? If a server is never empty, then we say that server is backlog. Okay, now why is this necessary? We'll get to this in a moment. So suppose if we assume that we have a constant rate server and server is never empty, then the total number of bits that come out of the system are r into t minus u, right? Because you're serving at a rate r and the interval is between t and u. So you will serve r into t minus u amount of packets, assuming that there are always packets to serve in that interval. So the departures between t and u would be equal to r into t minus. This is under the assumption that u comma t is backlog. Okay. Then we have dt minus du would be less than r into t minus u. The total amount of departures would be less than constant rate if it is not backlogged. I hope this is intuitively clear. Is not backlogged. Okay, so now suppose that we are at any time t. Suppose we are at any time t, and we want to see what is the last backlog period. Um, like the starting point of the backlog period if you are at time t. So the property for starting point of a backlog period is that as0 equal to ds0, right? If s0 is the start point of backlog. Okay, so mathematically, how do you write S0 is? You write it as sup S less than or equal to T such that AS equal to DS. So what you're doing is you have your time axis T, you have T, you're looking at all the values from 0 to T. So S is a variable which goes from 0 to T. And in all these places, you're seeing where at which S uh, there'll be multiple places where AS equal to TS, right? Multiple S's. So you want to see the maximum, the latest S, such that AS equal to DS. And from there to T, never has AS been equal to DS. So all these interval between here would be backlog. Right. So now we have defined S0 to be like this in a backlog period. Now let's call this equation as 1. Right. So from equation 1, we have dt equal to ds0 plus r into t minus s0, right? Okay, next we have, now we know that ds0 equal to as0 from definition. Therefore, dt equal to as0 plus r into ts0, right? So this is so what we're trying to build up is a relation between the cumulative departures, cumulative arrivals, and the service characterization. right? Why do we want to do this? The motivation behind this is we want to analyze systems as a linear system. So if you send A to a server S, you get a output D. And could I uh, write this as A convoluted with S equal to D of something of this form? Could I do this? This linear characterization of systems which are non-linear. But can I find a different definition of? Can I find a different definition of convolution where the system will become a linear system and I can use um, properties of okay. So now this equation, the main drawback of this whole equation is this whole equation depends on S0 and we might not be able to compute S0 always or might be a tedious job. So if S is less than, so what we want to do is we want to generalize the notion of F0. So we want to see if we can make something which if we can find a relation between D and A with respect to S. Here S is a concentrated server R of T minus S such that it is more easy to see it over all S than a particular S naught. So let's see if S is less than S naught, right? So suppose, yeah, if S is less than S naught, then you have, so then this is not a backlog period, right? Not a backlogged period. And and you'll have the second equation. This is the equation 2. So dt is less than or equal to ds plus r into t minus s. This is from 2. Okay. Now this is less than as plus r t minus s. This is from the fact that ds is less than or equal to as. Now, this directly comes from the assumption that there is no loss or creation of data in the server. And you can't create new data and send. So you always have to wait for a data to arrive to send. So always the number of arrivals would at most be the number of uh, the number of departures would at most be the number of arrivals. You can't have more departures than the number of bits that have arrived, right? So this is from the fact that ds is less than a, which comes from the implication no loss and server does not create data. Okay, so what you have from all of this is you have for s less than s naught, you have dt less than or equal to as plus r into t minus s, right? And you will retain equality. You will retain equality when s is equal to s0. Okay. Okay, let's take the case when s is greater than s0, right? So S is greater than S0, but it is still less than T. So S is something, a variable which goes from 0 to T. So let me make that clear before. So S belongs to 0 to T. It doesn't go more than T, but you have an S naught, which is the starting backlog period if you know your time T, right? Okay. So then you have AS is greater than or equal to AS plus dt minus ds. Okay, where does this come from? Now you are this also comes from 2, where you have RT minus S is greater than dt minus ds. Right. Yeah. Next, this is greater than or equal to dt. Why is greater than or equal to dt? Because AS and ds, these both. So AS minus ds is always greater than or equal to 0, right? So you are adding a positive term to dt. So this whole term would always be greater than d. That makes sense. Now, what do you get from here? Again, you get for s greater than s0, you get dt is less than or equal to as plus r into t minus s, right? So now for any s that is less than t and 0, you see that it satisfies this property of um, dt less than equal to as plus rt minus s, dt less than or equal to as plus rt minus s. Right. So rewriting these two equations, what do I get is dt is equal to inf of 0 less than or equal to s less than or equal to t as plus r into t minus s. So dt should be less than all the ss between 0 and t as plus rt minus s. So it should be less than the infimum of as plus rt minus s. Now, does this attain an infimum or not is a question that we'll answer later. Like, does this attain the infimum? If it does, when? Okay. Uh, if it does, when? These are all valid questions. We'll go through that. But what I want to concentrate on is the structure of this. So the structure of this equation, the structure is similar to a convolution. So the basic convolution that you guys know is you have an integration and you have some time shifted uh, version of a function into another function, right? Now, similarly here, instead of integration, you have an infimum, and instead of a multiply, you have a plus. You have the time shifted, time shifted and reversed. It's fine. D. And you have a function. So there are similarities between the convolution that we know and the equation that we have got here. But the only change is the plus sign is replaced by a minimum or an infimum that we have to see later whether it attains or not. The multiplication is replaced by an addition, right? These two major changes. But even then, does this convolution hold or not? So basically, we are talking of this as a service, not a curve, but let us assume that it is a service curve for now, for the constant rate service curve. So what will finally have is dt is equal to a convolution with beta, where beta is any service curve. So we want this property to be satisfied. So this all is done because now what I have is if I have a server which gives me a service called beta, which I know, and if I have an arrival, then I can find the departures process by just using convolution between A and beta. Okay. I hope most of the things are clear to you now. So, okay, what we try to start doing is we try to start modeling this real time system, and we came up with some pretty interesting result of how do you calculate the outputs given the inputs and the set, right? Okay, so next let me uh, process some give some definitions. So this definition is of a cumulative function, right? So I've said here these both are cumulative, right? You have cumulative arrivals, you have cumulative. What does cumulative mean? So the cumulative function is basically it's a function of a flow, right? So let me explain it using the function a. It maps from r plus to r plus, right? And what are the properties of these functions are it is non-decreasing, okay? And it is piecewise continuous, okay? And it is left continuous. Okay. Mm. And what we'll write is AT is the amount of data that has that the total amount of data that has arrived. So AT is the total amount of data that has arrived in the interval 0 to t. Okay. Um, Total amount of data arrived in this interval. Okay. Okay. So let me give you an example of an cumulative arrival curve. So till u, nothing is arrived, right? From u to u prime, 1 unit of packet has arrived, right? Now it could be that the 1 unit of packet has arrived throughout u to u prime, like the whole 1 unit packet was so big that it had to the start to finish of that whole one packet had to arrive from u to u prime, or it could just be that two packets of sizes one third and two third arrived in between the interval u and u prime, right? That is totally up to you. But in the interval u to u prime, 1 unit of packet has arrived at the so and so rate. U prime to V, nothing has arrived. V to V prime, again, we have um, another packet arrived. V prime to W, nothing has arrived, right? But there is a sudden instantaneous jump at V because a huge packet has, or 1 unit of packet has arrived instantaneously at W. So this is 3. So why we are doing it in this way is we want to model all the type of possibilities that can happen in a system, right? So there are discontinuities. There are instantaneous the discontinuities in the arrival process. So these discontinuities, right? So these discontinuities represent instantaneous arrivals. Okay. Uh, and one more important point to note is cumulative functions. They what do they represent? Like they represent only the total amount of data. They don't give any information of how big the packet was, how small the packet was, or how many packets there were there more or not. They just give a um, they just give uh, they give a total amount of data that has arrived till time. So okay, so after this, there are three major points that we want to discuss while modeling is one is choice of time domain. The next is use of cumulative data instead of throughput, right? The third is continuity of curves. So the first assumption, what is the time domain? The time domain here we have specified it to be r plus, but could it also take n plus n. It doesn't matter, but uh, what we want is we want a dense um, choice of time domain. This dense choice of time domain allows us to be more mathematically. It gives us more options in the mathematical domain, but in the real life system, most of the computers would work in discrete time. So you can work with discrete time or R plus. It's fine. There is no it is much it will be much it will be obvious that it will be much more convenient to work with R plus in network R plus, but sometimes you can work with N plus. That is also fine. That is not an issue. But these two are the main choices of your time domains. You can be either in discrete by choosing N, or you can be in the continuous domain choosing R plus. Right. The next is data. Why cumulative amount of data? Why not uh, throughput? This is mainly motivated by the mathematical requirements that network calculus has, right? So it is a requirement of the network calculus for us to work on mm, total amount of data, the total amount of data sent by the flow from the time origin till the current time t. That is what is defined for us. That is what we know, or some upper bound or some property of that we know. Whereas instantaneous throughput is not defined like in every time scale, because we also want to take into consideration any instantaneous arrivals, any huge packets which have instantaneous arrivals. If you want to model those, throughput basically does not give you the total amount. It just gives you an expected rate of arrival. So yeah, the choice of cumulative amount of data is done. But now this cumulative data, we have seen that there are three properties which come into it. One is non-decreasing. The non-decreasing part is clear because it's a cumulative amount of data, and no data is lost by the server, and no new data is created by the server. Under that assumption, you can see that as time increases, the total amount of data, because there are positive amount of data coming every time, the data would either be the same if no data has arrived, or if some data has arrived, the cumulative data would just increase. So that part is clear, right? So the part. uh, non-decreasing is clear. Next is piecewise continuous. So piecewise continuous basically comes because of this on off processes of sometimes there would be no flow arriving to the server, sometimes there would be some flow arriving to the server because of this nature, and there are some finite discontinuities when some instantaneous amount of packet arrives. So we want this to be piecewise continuous. That is just a modeling thing that you want to capture from the real system. As I have told here, you want to capture the most of the real world system that you can in your theory when modeling. So these two properties come under. Now the main part that we want to talk about is left continuous. Right. So left continuous. Okay. So basically the discussion on left continuous begins with what does AT mean? So AT can mean the total amount of arrivals in 0t, the total amount of arrivals in 0t, the total number of arrivals in 0t, and the total amount of arrivals in 0t. Which of these four um, we want to stick with so that we have some consistency in our math method that we're going to build up in the coming up classes. Okay, so basically these both are out because we want a0 equal to 0, but any instantaneous packet can be allowed to come at time t equal to 0. Now here where we get the main point of left continuous. So at 0 it will be 0, but then at 0 plus you will have a instantaneous jump. So to know that 0 plus instantaneous jump, you want your um, left side limit of your total to be 0 to know any instant whether any instantaneous value has occurred on it has packet has arrived at time t equal to 0, right? Okay, so now the discussion is between these two. So basically, to select these two, what we want to go back to is what we are interested in. For any s less than or equal to t, we are interested in the total amount of packets that have come between s and t. So this you can give by at minus as. This is what we want, right? And we also want to satisfy. So suppose s is less than t less than or u. We also want you to satisfy asu is equal to ast plus 8t, right? This is what we want to satisfy. So this is known as the Chasles equation, Chasles relation. We want our function, the function that we're going to model the arrivals with to satisfy the Chasles relation. Okay, so now suppose we say that AST is the total number of data that has arrived in this interval. Closed, both are closed, right? Then when you write AST plus ATU, you get ASU. Yes, but you also get T twice because here you have AST and again you have T to U. So you any packet which is arrived instantaneously at T you're calculating it in a s comma t, and you're also calculating in a t comma u. So you'll have a t comma t, but a t comma t could be positive, right? Because a t comma t is basically t comma t under the assumption that we have used this notation. Now there could be an instantaneous arrival at t. Again, there could be an instant, and a t t would be greater than zero, right? We don't want that. So so this also goes, right? And this is the only thing that is left. Okay, so now suppose we choose 0 to t, this one. Then you see AST plus ATU is equal to ASU. Eh, So here you have S to T. You have not calculated any instantaneous arrivals here, but the instantaneous arrivals go in this, in the second part, right? Here you just have a S to U. You have not calculated any U here, you have calculated U here, right? Now, if you want to calculate a t comma t, which basically is the amount of data that has come in t open close, this is basically the null set, right? Like it is an empty set. So you have nothing to calculate. So this basically becomes zero. So any a to t for all t greater than or equal to zero. Even a00 also is zero. So if you choose this, if you choose this type of notation, you'll see that everything follows, and a0 equal to zero. Similarly, d0 would also be equal to zero, right? Choosing this is what gives you the second implication that as comma t is a left continuous function from the definition. So choosing this gives us the notion that the cumulative function should be left continuous. But as we go into the math, we'll see that the whole theory of finding the upper bounds on this, it doesn't depend if it, even if it is left continuous or right continuous. It doesn't matter, but uh, the left continuous and right continuous matters in the sense of uh, you modeling the correct system to the correct theoretical model. The assumptions follow, right? So it need not be left continuous, it could be right continuous, and you can just change the openings of the bracket and you would be fine. Uh, right. Okay, so for today, I'll just give the definition of server. We have seen the definition of cumulative function, that is the arrivals and what all properties that it takes. Now how do you model a server that is left? So I'll just, for today's class, I'll just give you the definition of the server, and I'll continue from the definition of server, and we'll see how do we calculate delay bounds and backlog upper bounds using these things. Yeah, so we'll see that in the next class. So I'll just leave this class by stop this class by giving the definition of server. Right. So you have a server S. Now what is C? C is a class of functions, or you can say set of functions. which are all cumulative functions. This is from definition 1. Right. So a server basically is a subset of a relation between class of functions and is a total left relation between low cumulative functions. So how do you write as this? For all A belongs to C, there exists D. So these are apart cumulative arrivals. There exists a departure arrival such that A comma D belongs to S. So if you give A, there will always exist one D, at least one D. There could be many Ds. So that it belongs to the server thing. So uh, that satisfies A D belongs to S implies. And now when I say that it is a total left relation, it means that A is greater than or equal to D. This is also satisfied, right? So we can denote this in multiple ways. One denotation is ASD. So what is it? What this says is if there is a cumulative function, the server will give you a departure cumulative, right? A departure cumulative function. You can also write it as a set of A and D. A and D. This belongs to a tuple of A and D belongs to S. Okay, so when we say you have a left order, it means that it is pointwise order. Like for all t greater than 0, at is greater than dt. Right? So this is basically the definition of a server. We'll come back to it tomorrow in the next class. But yeah, that was today's class where we discussed some basic knowledge on single server and single flow stuff. I'll stop the recording. Thank you.